So hi everyone, good evening. We'll just wait for a minute and then we'll start the session. But today's session we will start with the questions on the photoelectric emission, because yesterday we have covered the theory part of the photoelectric effect, the Einstein's equation. As I remember telling you guys that mostly we'll get questions on the Einstein's equation of the photoelectric emission. So we'll continue with some problems on the equation for the photoelectric emission as per the Einstein's theory, and then we will go for the remaining topics. Okay. Hi guys. Yeah. So we'll just look at what is it that we were covering in the previous session. So in the previous session we were looking at the concept of electron emission. So just to quickly recall, right, we talked about three kinds of emission. One is emission by applying heat. We called it as what? Thermionic emission of electrons, where the electrons will get required amount of thermal energy so that they can come out of the metal, because for the electrons to come out of the metal they require a minimum energy called as what? Work function, which will be a property of the type of metal. Then there is one more emission which is achieved by applying a strong electric field. Okay, so that is called as what? Field emission. The third type of emission is basically the emission by using light. That is what we call as photoelectric emission. Okay, so the photoelectric emission or the photoelectric effect, right, is the phenomena which can only be explained by considering that light is made up of packets of energy quanta or particles, photons. So the strength of the particle theory of light is based upon the observation of photoelectric effect, because photoelectric effect can be explained only when we assume that light is made up of these particles or packets of energy. Clear guys? So in the photoelectric emission, right, we have seen what are the observations. So what factors will affect the photocurrent, what factors will affect the stopping potential. So what is it that we have observed? The photocurrent will depend upon the intensity of the light used. Photocurrent will depend upon what? Intensity of the light used. And the photoelectric emission happens only when the applied frequency is more than some threshold value. So only when the frequency of the radiation used is more than this threshold value, then only the photoelectric emission happens. And the stopping potential, right, it is representing what? Kmax. Stopping potential represents what is the maximum kinetic energy with which the electrons will come out. What is the relation? Kmax value is equal to E into V naught. Stopping potential value is equal to what? E into V naught. So the Einstein's theory proposed that a single photon will come and collide with electron, where the energy of the photon is absorbed by electron, and this energy h nu, because every photon will have how much energy? H into nu or h into c by lambda. This energy, a part of it will be used for making the electron to come out of the metal surface, that is the work function, and the remaining energy will be available as kinetic energy of the electron. So this is what we are calling as the Kmax. Why? Because some of the electrons, when they are coming out, right, internally they may undergo some collisions and lose some energy while they are coming out. So this equation is what we call as the Einstein's equation for the photoelectric emission. It is based upon what? That a single photon will collide with an electron, and if the energy is more than the work function, means the electron can come out. If the energy is less than work function, means the energy will be dissipated to the surroundings. So if you look at the energy of the photon, that will be equal to what? Work function plus the remaining part will be available as the kinetic energy with the electron. So this way the Einstein's theory was able to explain the observations of the photoelectric emission. What are the main observations? That the process is what? It's an instantaneous process. Immediately we see that the electrons are coming. Okay, And second thing is what? That the photo current depends upon the intensity, because as per the particle theory of light, intensity is given by what? Number of photons. More intensity means more number of photons, because we can see every photon can make one electron to come out. If the applied frequency is more than threshold frequency, means more number of photons are coming, means more number of electrons also can come out. So that way it is able to explain why the photo current value, right, is depending upon the intensity of the light. Okay, and the third observation is what? The stopping potential value will depend upon the applied frequency. Okay, so this we can see based upon the equation, because if you look at this energy of the photon, h nu is equal to what? Work function plus k max. What is k max? E into stopping potential. So we can see that stopping potential value will depend upon what? It will depend upon the applied frequency as well as nature of the metal. Why? Work function will be depending upon the nature of the metal. Work function will be changing from metal to metal. So this is what we were covering in the yesterday's class, guys. We'll start with and of course one more thing before we go on to the problems. The frequency which can make the electrons to just come out. Exact frequency, right, which can make the electrons to just come out. That frequency is going to be called as what? The threshold frequency. Means the energy will be just sufficient to make the electron to come out. So h into nu naught will be equal to what? Work function. So when you apply frequency which is equal to threshold frequency, electrons can come out, but they will come out and just stop. They will not have any more kinetic energy with them. Clear, guys? So this is what we were covering in the yesterday's class. Now let's just start with some questions on this. Look at this question, guys. The photoelectric cutoff voltage. Remember what I said? Cutoff voltage is the other name for what? It is the other name for the stopping potential. Cutoff voltage is the other name for what? Stopping potential. The photoelectric cutoff voltage in a certain experiment is 1.5 volt. Means what they are giving us? They are giving us the stopping potential value. What is stopping potential value? 1.5 volt. Okay. What is the maximum kinetic energy of the photoelectrons emitted in joules? What they are asking? They are asking what is the maximum kinetic energy of the photoelectrons emitted in joules. Remember, guys? Ritesh, hi. So remember what is the formula? What is the formula, guys? The K max value is equal to what? E into stopping potential, correct? K max is equal to what? E into stopping potential. What is this E? E is the basic charge. What is the basic charge, guys? 1.6 into 10 to the power of minus 19 coulombs. What is the basic charge value? 1.6 into 10 power minus 19 coulombs. I think Shyam, you are able to get the answer. So they are asking what? The maximum kinetic energy of the photoelectrons. Means what we have to do, guys? What we have to be doing? This 1.6 in 10 power minus 19 coulombs into what is the stopping potential? Remember, guys, stopping potential other name is what? Cutoff voltage. What is stopping potential value they are giving us? 1.5 volt. Remember what is coulomb into volt? Joule. Coulomb is the SI unit of charge, volt is the SI unit of voltage. Coulomb into volt is what? Joule. 1.6 into 1.5. Check it, guys. I think we are able to get the answer. 1.6 into 1.5 is what? It will be 2.4 into 10 raised power minus 19 as it is. So check this one up, guys. What is the answer? 2.4 into 10 to the power of minus 19. I think Tasneem, Keshavan, Amoga version. So Amoga version, you are a little bit late today. Okay. So check this one out, guys. What is the answer? 2.4 in 10 power minus 19. In terms of joules. They are asking in terms of the joule unit. Okay. Clear, guys? So the problems in dual nature will be coming only from the Einstein's equation. So what are the main formula we have here, guys? We have the relation between the work function and threshold frequency. What is the equation? Work function is equal to h nu naught. Equation 1. Then we have the equation between what? The maximum kinetic energy of the electron and stopping potential. Okay, K max is equal to what? E into V naught. V naught is what? Stopping potential, also called as what? Cutoff voltage. Then we have the Einstein's equation. H nu is equal to what? Work function plus K max. So if at all we are getting any questions on this chapter, right guys, we will get questions only based upon these three formulae. Okay, I think most of us are able to Sri Harimurthy. Okay, so you are also able to get the answer. Let's go to the next question, guys. So what is the answer for this one? 2.4 into 10 power minus 19 joules. Okay, let's look at the next one. Look at this question, guys. The work function of cesium is 2.14 volt. What is the work function of cesium? It is 2.14 electron volt. Work function is what? It is representing energy. Work function represents what, guys? Energy. Work function is given as what? 2.14 electron volt. Remember, generally the work function values will be given in what? The atomic energy, the energies in the atomic range, right? We'll talk in terms of the electron volt. But we can convert. What is the conversion? 1 electron volt is equal to what? 1.6 into 10 power minus 19 joules. What we need to find? Find the threshold frequency for cesium. What we have to find in this question, guys? Ryan, hi. Okay. What we have to find? We have to find the threshold frequency. What is the formula, guys? Work function phi naught is equal to what? H into nu naught. Work function phi naught is equal to what? H into nu naught. H is what? Planck's constant. This nu naught is the threshold frequency. Means nu naught is equal to what? Work function by H. What is work function, guys? 2.14 electron volt. If you want to get the threshold frequency in hertz, means SI unit, we should convert everything into SI system. Work function is what? 2.14 electron volt, right? Means into 1.6 into 10 power minus 19 will come. We are converting this into joules. We are converting this into what, guys? Joules. Okay. Divided by H. What is H? Planck's constant. 6.626 into 10 to the power of minus 34 joule into second. What is the Planck's constant value? It will be 6.626 into 10 to the power of minus 34 joule into second. That is the value of the Planck's constant. So they are giving us work function and they are asking us to find what is the threshold frequency. We have the formula. What is the formula? Work function is equal to what? H into nu naught. So nu naught will be equal to what? Work function by H. In this we have to just take care of the conversion of units. We have to take care of the conversion of units. So we can see here, guys, joule and joule will be cancelled. Joule and joule will be cancelled. Then you know the frequency is going to be coming in what units? Hertz. The frequency is going to be coming in which units, guys? It will be coming in the units of hertz. Anandita, okay. You are saying it is 0.51 into 10 power 15 hertz. Okay. Check it, guys. Others. I think Sham, you are also saying 0.516. Okay. So Arvind, you are rounding it off and then saying 0.52 into 10 power 15. Keshavan, you have to check your answer because others are giving different answer. Okay. So check it, guys. It's a straight formula question. So all these three chapters, dual nature, atoms and nuclei, we have straight formula based questions. Gunavati, hi. Okay. So check this one, guys. What will be the frequency value? Frequency will be equal to what? 5.16 into 10 power 14 hertz. So some of you are getting 0.516 into 10 power 15 hertz. We can convert this into scientific notation. What is scientific notation? The number part will be between 1 to 9.99 and so on, and there will be exponent part. So 0.516 into 10 power 15 hertz, right, can be also expressed as what? 5.16 into 10 power 14 hertz. It can be written as what, guys? 5.16 in 10 power 14 hertz. Madhukeshwar. Okay, I think you are coming after a lot of time anyway. So what is the name you have kept? Choco fluoride mad, huh? MSD, sorry. Okay, fine. So what is the answer for this question, guys? So these problems, right, again I am reiterating, We have three formulae. What are the three formulae we have? Work function of a metal is equal to what? H into nu naught. Nu naught is what? Threshold frequency. Then when the electrons are emitted by the metal, maximum kinetic energy of the electrons emitted will be equal to what? E into stopping potential. E is basic charge. Then the third equation is what? The energy of the applied photon, h nu is equal to what? Work function plus k max of the emitted electrons. These are the three equations. Okay. What are the three equations, guys? First is what? Work function is equal to the energy of the photon with threshold frequency. That is the first formula. Second formula is what? The maximum kinetic energy of the emitted electrons is equal to what? Basic charge into stopping potential. And third is what? Third is the applied energy, photon energy is equal to what? That will be used for making the electron to come out, work function value, plus the remaining energy will be as the kinetic energy of the electrons emitted. Clear, guys? Clear with this? Okay. So Aditya, hi. So what is the answer for this question? 5.16 into 10 power 14 hertz. Let's go to the next question, guys. This is a little bit more numerically, I don't call it as a challenging question, but it involves two calculations we can see. Look at this question. Work function of cesium metal is 2.14 electron volt. Means they are giving us what, guys? Work function of the cesium metal is given. Work function is given to us. Okay. When light of frequency 6 into 10 power 14 hertz. What is the frequency of the light that is used here, guys? 6 into 10 to the power of 14 hertz is incident on the metal surface. When this much frequency light is incident on the metal surface, photoelectric emission happens. Photo emission of electrons occurs. Then what is the maximum kinetic energy of the emitted electrons? That is the first thing we have to find. What is the first thing we have to find? We have to find what is the K max value. Second thing is what? Stopping potential. It's clear, right? See, once you get the K max value means we have the formula, right? What is the formula? K max is equal to E into stopping potential. So if you get A answer means using that we can find the B answer also. Clear, guys? If you get the A answer means we can find the B answer also. Okay. I think Sham, you are getting some, okay. Sham, you are saying for A, it is what? 0.34 electron volts. Tendril, high. So for B, you are saying 0.34 volt. Check this one out, guys. What is the given information to us? Work function is given, frequency is given. So look at this, guys. Work function of the metal is given. What is it given as? 2.14 electron volt. What is the work function given to us? 2.14 electron volt. Okay. Now the frequency is given to us. Frequency of the radiation. What is it? 6 into 10 to the power of 14 hertz. What is the frequency here given to us, guys? 6 into 10 to the power of 14 hertz. Okay. Now what we need to find here? What do we need to find, guys? We need to find the maximum kinetic energy of the emitted electrons. Look at this. What is the Einstein's equation for the photoelectric emission? The energy of the radiation that is incident, h nu. Again, guys, it's a very simple formula. What is it? We are incidenting a light. What is the energy of quantum? One packet energy is what? H into nu. This will be used to make the electrons to come out. Means a part of this will go into work function requirement, because work function is what? Energy required to remove the electron from the metal surface. The remaining part will be going into, once the electrons come out, right? The remaining energy will be existing as the kinetic energy of the electrons. That is what we are calling as the K max. Why K max? We are saying some of the electrons inside the metal itself, right? When they are coming out, they may lose some energy because of collisions. So as per this equation, right, what is the K max value? K max value is equal to what, guys? H nu minus work function. What is K max value? H nu minus work function. So here we have to take care of the units, because work function is given in what? Electron volt. Frequency is given in hertz. So can we convert everything into SI unit? H is what? 6.626 into 10 power minus 34. Okay, we are taking everything in the SI system. Frequency is what? Into 6 into 10 power 14. So H into nu will be coming in joules. H into nu will be coming in what, guys? Joule. Okay. And what is the work function? 2.14 electron volt. How do you convert electron volt into joules, guys? How do you convert electron volt into joules? 1 electron volt is equal to 1.6 into 10 to the power of minus 19. We have to multiply by the electron volt energy. We have to multiply by what? The conversion factor. What is the conversion factor? 1.6 into 10 power minus 19. Okay. So check this one out, guys. I'll just erase some of the things so that it will be clear. So I'll keep the equation. I'll just erase the given information. Okay, because this is already, I'll erase this part also. Check this one out, guys. So what do we have? We just have to perform the calculation. So it's a straight formula question, guys. H into frequency is minus work function. We are converting everything into the SI system. We are converting everything into the SI system. Go P high. So we are converting everything into what, guys? SI system of units. So here the Kmax is going to be coming in what? Joule. Kmax value is going to be coming in what, guys? Joule. I think a lot of you are giving the answer in electron volt, but anyway. So look at this, guys. Those who are able to complete the calculation, right? So first here 10 power minus 34 in 10 power 14, which is what? 10 power minus. So what you are having, guys? 6.626 into 6 into 10 power minus 20 will be there. This is what? 2.14 into 1.6 minus 2.14 into 1.6 into 10 power minus 19. So this we have to simplify. This value we have to simplify. Okay. I think we are getting some responses, guys. Keshavan, you are saying it is 5.51 into 10 power minus 20. So what is the thing we can do? First we can convert both of them into what? The power of 10 is minus 20 and minus 19. We can convert into 1. We can convert both of them into what? We can convert both of them into the 10 to the power of minus 20. Okay, I'll erase this part, guys, so that we can do the calculation by having space here. Okay, since I'm assuming you would have noted down the formula already. So now we have to just do what? 6.626 means we have to multiply. 6 6 are 36, 6 2s are 12, means 13 will come. 36 again 7, 3, 39.736 into 10 power minus 20. So here we can write as what? 21.4 into 1.6 into 10 power minus 20. So we will take the 10 power minus 20 common. 39.736 minus 21.4 into 1.6 into 10 power minus 20. This will be in what? Joules. I think this is what some of you are saying. Avantika, hi. Okay. So this is what you are saying, guys. What is it you are saying? You are saying this value is what? 21.4 into 1.6. So you can perform this calculation also, guys. I mean, first forget about the decimal places. 16 4s are what? 64. So we'll have 6. 16 1s are 16. Means 22. 2 will come. 16 2s are 32. Means after putting decimal places 34.24. 39.736 minus 34.24 into 10 power minus 20. So what will be the answer, guys? It will be 5 point something. Check it. It will be what? 5 point something in 10 power minus 20. Otherwise 0.548 into 10 power minus 19. So if you do this one, you are going to get what? I think you will be getting 5.48 into 10 power minus 20, which can be also written as what? The answer they are giving is what? 0.548 in 10 power minus 19. Either ways. Clear, guys? So this is how we will find the Kmax value. Once we get the Kmax value, what is the next thing they are asking? They are asking what is stopping potential. What is the formula, guys? Kmax is equal to what? E into stopping potential. E is what? Basic charge. What is the step here, guys? Kmax is equal to what? E into basic E into the stopping potential. So we have the Kmax value. Kmax value we have, and E value we know. What is E? Basic charge. What is basic charge? 1.6 into 10 power minus 19 coulombs. What is basic charge, guys? 1.6 in 10 power minus 19 coulombs. Means from here we can find out what is the stopping potential value. Check this one out, guys. What is stopping potential value? From here, what is the stopping potential value? Kmax by E. So what is Kmax? 0.548 into 10 power minus 19 joules divided by E is what? Basic charge. Basic charge is 1.6 in 10 power minus 19 coulombs. Okay. Joule per coulomb is what, guys? Volt. Joule per coulomb is what? Volt. So 10 power minus 19, 10 power minus 19 is cancelled. 0.548 by 1.6 volt. So check this one out, guys. What will be the answer? I think a lot of you are able to get the answer. What is the option B, guys? 0.34 volt. Case 1 you have to check. It is not electron volt, it is what? Volt. What will be the stopping potential? It will be, it's a voltage, right? It will be having units of, SI unit of potential is what? Volt. Clear, guys? So first what we did, just to summarize the problem, what we have done in the first step, guys, we used the Einstein's equation. Energy of the photon is equal to what? Work function plus Kmax. This is the formula we have used. Energy of the photon is equal to what? Work function plus Kmax. From here we are able to find the Kmax value. It's a straight formula substitution. H nu minus work function. We got the Kmax. Then we are using this formula. Okay. Clear, guys? So what is the stopping potential value? 0.34 volt. Now so far, right, we have been discussing about the idea of the experiments that support the particle theory of light. So what we said, the photoelectric effect is the major phenomena that supports the particle theory of light. Strictly in our syllabus, right, as per the JEE or NEET syllabus, or even the NCERT syllabus for that matter, we will cover only this one. So we have to cover only the photoelectric effect. But sometimes, in some examinations, right, they can even ask what are the other phenomena that support the particle theory of light, because particle theory of light is not only explained by the photoelectric effect, but there are other phenomena also that can be explained only by using the idea that light is made up of particles. So what are these other phenomena? The other phenomena are the low energy phenomena is what we have seen so far. Means we use the radiation of low energy. Typically this is what your X-rays and UV rays. In the photoelectric emission phenomena, right, typically what is the light that is used? We use X-rays and UV rays. Then there will be the mid-energy range phenomena. Means we use radiation of middle energy range. Means typically the gamma rays. The low energy gamma rays. Gamma rays are the highest energy radiation. Gamma rays will have, among all the electromagnetic radiation, gamma rays will have the highest energy and highest frequency. The middle energy phenomena will be about what? The low frequency gamma rays. Gamma rays are having highest frequency. In that also we have low frequency gamma rays and high frequency gamma rays. So in the mid energy phenomena, right, we have two experimental observations. One is called as Thompson effect and second is called as what? Compton effect. What are these, guys? So it's sufficient if you know the names of these. Okay, so we don't really need to go and detail out what are these effects. So what are the other phenomena that support the particle theory of light? One is what? Thompson effect. Second is what? Compton effect. These two will happen in the middle energy range. Then we have phenomena that happens in very high energy range. That is only possible with gamma rays which have very high frequency. So these experimental observations also, right, we can explain them only when we assume that light is made up of particles. We cannot explain these observations by considering light as a wave. Just like, the photoelectric emission can be explained only when we assume light is made up of particles. We cannot explain the photoelectric emission by considering light is wave. Same way, Thompson effect, Compton effect, and the third is what? Pair production. What is the third phenomena, guys? Pair production. This phenomena also can be explained only when we assume that light is made up of particles. Now what we'll do is, we don't need to learn about these things in detail, but since we are anyway, there is no point in just knowing the names. Sometimes we may even forget them also. Though it is not exactly there in the syllabus, right? We'll quickly take a look at what these phenomena are. So first we are going to begin with Compton effect. Compton effect and Thompson effect, right? Thompson effect and Compton effect, they both will be in similar manner. Look at this, guys. What is this Compton effect? It is interaction between electron and photon. Means you can see a gamma ray photon is coming and hitting electron. You can see gamma ray photon is coming and hitting electron. What is happening? The electron is going in one direction and there is another gamma ray going in the other direction. Look at this, guys. The interaction between electron and photon, right, results in electron being given a part of the energy. Means the gamma ray, the photon will have some energy. The photon will have some energy. Okay. Some part of the energy will be given to electron. The remaining part of the electron, right, the remaining part of the energy will be emitted in different direction as another photon. So one photon is coming and hitting the electron. The electron will move in one direction. The remaining energy, and for the electron to move, it will require some energy, it will take some energy. The remaining energy will be given as another photon which goes in different orientation. Now this phenomena, right, has to satisfy the conservation of momentum. That's why if the electron is coming in one way, right, the other photon is going to go in the opposite direction, because it has to satisfy the conservation of momentum principle. Clear, guys? So this observation is what we call as the Compton effect or Compton scattering effect, because here what is going to happen is the gamma rays will be what? Scattered. The gamma rays will be what? Scattered. As they hit the electron, the gamma ray, original gamma ray will not come, or the original gamma radiation will not come. The radiation that comes will be of different frequency. This one, right, the scattered gamma ray will have a different frequency. If the original frequency is nu, it will have a different frequency, nu dash. And what is the conclusion? Nu dash will be less than nu. Means some energy is given to electron, the other energy is coming as what? It is coming as the another gamma ray. So this satisfies the conservation of momentum principle, and this can also be explained only when we consider that the light is made up of particles. You cannot explain the Compton effect by considering that light is a wave. Clear, guys? So this is the Compton effect. Okay, so it's we don't need to get into the too much of details of it. It's sufficient if we understand that, okay, there are other phenomena which can be explained also only when we consider that light is made up of particles, because there are a lot of experimental observations that support the wave nature of light. What are these experimental observations, guys? Interference, diffraction, and polarization. I think if you would have gone through our first lecture, right, you would be knowing what are these phenomena: interference, diffraction, and polarization, right? These observations, they can be explained only when we consider light is a wave. Photoelectric emission, Thompson effect, Compton effect, and then pair production, they can be explained only when we consider light is made up of particles. So that is the reason why we have to accept the dual nature of light. Okay, so this is Compton effect, guys. Now let's go to the pair production. So what is the pair production? Pair production is a very simple idea, guys. If you have very high energy gamma radiation, very high energy, this cannot happen because of less energy radiation. A very high energy gamma radiation, right, it is going and interacting with the nucleus. Typically this happens where when the very high energy gamma photons or gamma radiation, they interact with the nucleus. As a result of this, right, we will produce pair of particles. Actually, we will produce a particle and its antiparticle. What is this antiparticle concept? We will study in the nucleus chapter. But here, just to give you the idea, right, the particle and antiparticle, like we have electron. The antiparticle for electron is what? Positron. What is the antiparticle for the electron? It is what? Positron. Then we have proton. So we have antiproton. This is the antiparticle. Then we have some other, subatomic particles called muons and neutrino. So for every of these subatomic particles, right, we can have the corresponding antiparticle. Okay, so we will learn about what is the antiparticle, etc. But just to tell you, right, very brief idea, if you have electron, what will be the charge? -1. Electron will have a mass. What is the mass of electron? 9.1 in 10 power minus 31 kg. A positron will have exactly +1 charge. Mass will be similar. This is different from proton. Why? Because proton mass will not be equal to electron mass. Positron mass will be equal to electron mass. So the positron and electron, they are called as what? Particle and then antiparticle. So when the very high energy gamma rays, they go and hit the nucleus, what we observe? We will observe the formation of pair of particles. One is a subatomic particle, and what will be the other particle? It is the antiparticle. We can see if electron is coming, then what is coming on the other side? Positron. Here also the conservation of momentum principle will be balanced. Means, we can see that if the electron is going in one direction, the positron will be going in the other direction. So the pair production rate, it has to satisfy both the conservation of energy principle as well as conservation of momentum principle. This can also be explained when we consider that the gamma radiation are coming in the form of the particles or photons. Okay, so the photoelectric emission, Thompson effect and Compton effect, the scattering effect, and pair production. All these experimental observations, right, we can only explain them when we consider that light is made up of particles and not wave. Okay, so this is about the experimental support for the particle theory of light. Because in the beginning of the session itself, I told you guys, in the beginning of the chapter itself, this chapter, right, generally we know light means what we consider light is a wave. But here we are going to be focusing on what? Since we are talking about the dual nature, we are going to be focusing on what? We are going to be focusing on the particle nature of light. And we have seen what are the experimental observations that support the particle nature of light. And the other side of the story is, whenever we say matter or particles, we will not associate any wave phenomena with that. But de Broglie gave the concept of matter waves. So where as per the de Broglie theory, what we have understood, every moving object can be having a wavelength. We even saw the formula for the wavelength of the matter waves. So we will have to see what are the experimental observations. What are the experimental observations that support the wave nature of matter? So far what we are seeing, what are the experimental observations that support the particle nature of light? And now we have to see what are the experimental observations that support the wave nature of particles. And here, right, the particles that have initially successfully shown the wave nature or wave characteristics are electrons. So most of the initial experimental studies, right, they were performed on what? They were performed on electrons. So if you are wondering, right, what is there on my back screen? So these are the these are the scientists who are setting up the experimental setup that has resulted in proving that the electrons are actually having wave nature or wave characteristics. Okay, so the scientists whom you are seeing on the picture, right, they are basically who? Davison and Germer. So Davison and Germer, they have done experimental studies to prove that electrons can show one of the important phenomena that is given by light, which is diffraction. So Davison and Germer, they have proved that electrons can also show what? Diffraction phenomena. The same thing was later independently, not along with them, independently also proved by GP Thompson. So if you are wondering, right, who is this GP Thompson? So the guy on the left side is JJ Thomson. Okay, so JJ Thomson is the scientist who has discovered electrons. He has received a Nobel Prize for the discovery of electrons, where he said electrons are what? Negatively charged particles. The fellow on the right side, right, this is the guy GP Thompson. So GP Thompson is in fact the son. He is son of JJ Thomson. He is son and also his student. Okay, so GP Thompson, he also experimentally proved. Davis and Germer, they proved the wave nature of electrons, where they have demonstrated that electrons are able to have the diffraction phenomena. GP Thompson also independently proved that electrons can show diffraction phenomena. So both GP Thompson and Davison, right, they combinedly were given Nobel Prize for proving the wave nature of electron. So if you look at it, right, I mean the ironical thing is, like, when father says that electrons are made up of particles or electrons are having particle nature, son is saying that is wrong, and the electrons in fact are having what? Wave nature. So both, I mean, the interesting thing is both of them have got Nobel Prizes. So the idea is all these experimental observations, right, they have led to the discovery of the diffraction phenomena, which is shown by electrons in crystals. Okay, so typically the nickel crystals are used. Nickel crystals are used where electrons will show diffraction when the electrons will go through the small, because every metal, right, in solid state chapter of chemistry you might be studying about it. If you look at every metal crystal, there will be some voids. What will be there in every metal crystal? There will be some voids. What are voids? Voids are basically interstitial sites. There will be some gaps. So the electrons, when they go through the gaps, right, electrons when they go through the gaps, because when light is going through a small opening, what does the light will be bending? That is what we call as diffraction. Remember, when light is going through a very small opening, it will bend. That phenomenon is called as diffraction. So here the electrons are going through small voids. Then electrons also exhibit what? Diffraction. That is what is proved by the Davison and Germer experiment. Okay, so let's quickly take a look at this experimental setup, guys. So here we don't have any equations. We just have to understand what is the experimental setup of Davison and Germer and their conclusion. So this is the setup we are going to have. So we have what we call as an electron gun. So electron gun is nothing but it's an LT. LT basically means low tension. Okay, so basically low voltage. So we produce electrons at a lower voltage, and then we will pass them through a region which is connected to what? High voltage. Typically, what is the range of the high voltage? 44 to 68 volt. So we don't need to remember these values, just understand the procedure. We'll produce the electrons at low voltage, we'll accelerate them. So when we accelerate them, right, what we'll get? Electrons which are now moving at relatively higher speeds. Now what we'll do is the electrons which are now accelerated, right, they will come with a desired velocity. Means whatever the velocity we want the electrons to achieve, they will now be coming with that particular velocity value. These electrons, right, will make them to pass through a cylindrical kind of an opening area with fine holes. So here we see, right, there will be a cylindrical kind of an opening with fine holes. Small holes will be there. What this will do is it will produce collimated beam. Collimated beam means, like, the electrons are coming in one single beam. It is not like the electrons are coming in all different directions, because when the electrons are emitted from the filament, right, they will start going in all different directions. We first accelerate them, then we allow it to go through a cylindrical path where there will be small openings, and the electron beam can only go in straight line from the openings. So this will give rise to what we call as collimated beam of electrons. This will go and fall on the target. What is the target? It is the nickel crystal. The target is what? Nickel crystal. Now what happens when it hits the target? Generally what we observe, if say for example electrons are particles, what is going to happen when you throw the particles onto some metal surface? What we expect? The electrons will be getting scattered. The electrons will be getting what? Scattered. And how it should get scattered? It should get scattered randomly. The electrons should get scattered randomly. Okay. But here the observation is when you try to measure the photocurrent. Photocurrent is what? The current because of electrons coming. So when you try to measure the photocurrent by using what? The intensity of the scattered beam. So the electrons are coming here. So we can see there is a movable collector. Movable collector means we can keep on moving it. We can keep on moving it along a circular path. We can keep on moving it, and at different angular positions, right? At different angular position we can keep on measuring what is the photocurrent value. Generally what we expect, if the electrons are randomly scattered, what do we expect? We should see that the photocurrent value will be always same across different places. It should be almost same across different places. But that is not what people observed. What they observed was that at a certain angle, like if you are using the accelerating voltage as 54 volt for a specific value of the voltage, what is the accelerating voltage that is used? A particular value 54 volt. Okay, if you use this voltage, then what they observed is the peak value of that photocurrent. Means maximum number of these electrons are coming at a direction where theta is equal to what? 50. The maximum number of electrons are coming at a direction where theta is equal to what? 50. Now this phenomena, right, can only be explained if you consider that electrons are actually behaving as a wave, where normal particles means what? They will undergo uniformly, they will get scattered in all different directions, but that is not happening. In one direction we see that the particles are going with maximum intensity. So that is explained by what we see generally in the wave phenomena. What is it? When there is interference. When we will get a maximum, if you have waves, when there is interference, if the two waves are adding constructively, what do we call this as? Constructive interference. Then at that place we are going to get what? Maxima. If the two waves are adding constructively, then at that place we are going to get what? Maxima. So at a particular angular position we are getting a maxima, means this must be what? The position where we are getting the constructive interference. So they didn't stop there. Okay. So they have understood that the peak value is because of what? The constructive interference of the scattered electrons, and they have even measured using the diffraction equation, right? So we will learn about what is the diffraction equation in wave optics chapter. Here it is not required for us. Using the diffraction equation, they've even measured if you have to get a maximum at angle 50. If you have to get a maximum at angle 50, what should be the wavelength of the light? If you are really, instead of using electrons, we are using light, which is having a wave nature. If you have to get a maximum at angular position 50, what must be the wavelength of the light used? So as per the calculation, right, what they have got the number as what? 0.165 nanometer. So if you use a light of this much wavelength, then as per the diffraction, right, we are going to get a maximum at theta is equal to 50. Here we are not using light. What we are using? We are using electron beam. Electron beam is also giving a peak, where it is giving peak at the 50 degrees. And how do they correlate this, the wave nature of electrons? If you actually use the de Broglie concept. What is the de Broglie concept? It says every moving object can have wavelength. What is the wavelength formula? Lambda is equal to h by p. Remember guys, we have the alternative formulas. Lambda is equal to h by p, or h by m into v, or h by root 2m into kinetic energy. These are all the alternative formula we have seen. Or h by root 2m in place of kinetic energy. If you have a charged particle which is accelerated through a potential v, then the kinetic energy of the charged particle will be equal to what? Q times of v. So this is the formula we can use. For lambda, what is the formula we can use? H by root 2mqv. If you remember, we have done for electron, because for electron mass is fixed, charge is also fixed. We have a simplified formula. So we are not using any different formula, guys. We already seen this formula in previous class. What is the lambda value for the electrons? 1.227 by root voltage, and the lambda will be coming in what? Nanometers. Go back and check it, guys. We have seen this formula already. If you are accelerating electrons, for which we know the mass, we know the charge, we already know the numerator, Planck's constant also we know, then the formula will be just coming in terms of what? Voltage. What is the formula we have seen, guys? Lambda will be equal to what? 1.227 by root V. The lambda will be in what? Nanometers. If you use the V value is 54 volt, because what is the voltage which we use for accelerating electrons? 54 volt, right? If you put V is equal to 54, right, then the lambda for the electrons is exactly coming as what? 0.167 nanometer. What is the lambda for the electrons coming as what, guys? 0.167. Previously what we said, if we have to get a maximum at theta is equal to 50, then as per the diffraction calculation, right, what we concluded, the wavelength of the light must be coming as what? 0.165, which is almost same as the de Broglie wavelength of the electron. This is almost same as what? De Broglie wavelength of electron, which means what? The electrons are exactly behaving like a wave. Whatever the diffraction that the light is able to show, because if you pass, instead of electron beam, we are passing light through the nickel crystal, then at 50 degrees angle, we are getting a maximum, means what will be the wavelength of the light used? 0.165 nanometer. Instead of using the light, here what we are using? Electron beam, which is accelerated by using a potential of 54 volt. As per the de Broglie theory, we have a formula for the wavelength of electron. What is it? 0.167 nanometer it is coming. And the electrons are also exactly showing the same diffraction behavior. So this is how they are able to conclude that electrons can have the wave nature. Okay. So and this has settled the idea that the dual nature is not only for the light. Dual nature can be described also for the particles. But just remember what de Broglie has proposed in his theory. The dual nature or the wave nature of particles will be significant. This we should not forget. The wave nature will be significant. When the wave nature is significant, it will be significant when the lambda that we derive, right, is comparable. It should not be equal, but it should be comparable. It should be comparable to the dimensions of the object. So whatever the object we have, right, like say for example, we talk about a cricket ball moving. Using the formula lambda is equal to h by mv, right, we can find the wavelength of the cricket ball also. But is it going to show a wave nature? Probably not. We will still see the cricket ball as a cricket ball only. Why? Because the wavelength that you get may not be comparable to the size or the dimensions of the cricket ball. Usually for the subatomic particles like protons or neutrons or electrons, when they are moving, right, the wavelength will be becoming comparable to the dimensions of the particles. That is why they tend to exhibit the wave nature more visibly. We can observe, like the electrons, we can observe them performing diffraction phenomena. But normal cricket balls, if you throw, means we will not observe them seeing diffraction phenomena. Why? Because the wave properties will be significant only when the wavelength of the particle that you find as per the de Broglie formula is comparable to the dimensions of the object. Clear, guys? So this is what is the Davison and Germer experiment. Now as a last part of this chapter, right, we have the idea of X-rays. Okay, but the X-rays will cover anyway in the next chapter also. The structure of atom, or the atoms chapter also will cover that. So here we'll just quickly take a look at what are these X-rays. Remember, guys, X-rays are basically the radiation which are produced. What are X-rays? X-rays are the radiation which are produced when accelerated electrons, right? When accelerated beam of electrons, when they go and hit a metal. Okay, so typically if you look at the visualization here, right, the visualization that I am marking on, so we will produce the electrons at the cathode. If they are accelerated and they will come and hit the anode, what happens is, with the anode is what we call as the target metal. Anode is called as what? Target metal. Okay. What happens is, these electron beams, right, they'll have a lot of energy. Most of the energy that the electrons bring will be dissipated as heat. We can see heat is basically marked over there. Most of the energy will be dissipated as what? Heat. Only a small portion of the energy will be emitted as what? X-rays. And that is the reason why whenever we are using the anode or the target produces X-rays. The target metal should generally have high melting point. In fact, this was a question in one of the previous year examinations also. The target metal must be having what? High melting point. Otherwise, what happens? Since most of the energy is getting converted into heat, then the metal will obviously melt out. So it should not have low melting point. It should be having very high melting point. Then we will see the X-rays being produced by the metal. And in the right side visualization also, you can see here, when the electrons are coming and hitting, right, what you are producing? You are basically producing the X-rays. And scientists have studied the properties of the X-rays. In fact, Moseley, who is credited for the discovery of atomic number, he was able to get the idea of atomic number from the properties of the characteristic X-rays. We will see when we discuss about the X-rays in detail. So he came up with an empirical formula that the frequency of the X-rays, right, root mu will be equal to A into Z minus B. This is the formula that Moseley has come up with. We will discuss about this formula when we talk about the X-rays in detail, but he was able to come up with an empirical formula. What is it? This empirical formula is like in atoms chapter we will see when we talk about the spectral lines, right? The spectral spectrum of different elements. There are some empirical formulae that are given. Lyman series formula, Balmer series formula, Paschen series formula, bracket. All these different spectral line formulas are given. We will call those formulas as what? Empirical formulas. So any formula which is designed to satisfy experimental data is called as what? Empirical formula. So Moseley has proposed an empirical formula that satisfies the frequency of the X-rays emitted by the target metal. So this anode is called as what? Target metal. The frequency of the X-rays emitted, right, will depend upon this Z value. Z value will depend upon what is the target metal. Okay. So for say for example different metals, right, the Z value is different. And this Z is what later been called as what? Atomic number. This Z is what later called as what? Atomic number. This number is a characteristic of a particular type of metal. And later, this is seen as the basis for the chemical properties of the elements, and that is the basis for the modern periodic law, and so on and so forth in chemistry. Okay. So this is about the idea of X-rays, guys. We are not going to discuss about the details of the X-rays because we will discuss about them in the next chapter, atoms. But just the idea of how the X-rays are produced. How the X-rays are produced? When we have the accelerated beam of electrons, they come and hit the target metal. Target metal must have a high melting point. Why? Because most of the energy of the electrons will be converted into the form of heat. Large dissipation, more than 95% will be what? Dissipation. Small fraction of energy is only changed into what? X-rays. And these X-rays, right, the properties of the X-rays, frequency of the X-rays will be depending upon what? The nature of the target metal. And Moseley gave the empirical formula for the frequency of these X-rays, which has led to the discovery of the atomic number of the respective elements. Okay, so we'll talk about this in the atoms chapter, guys, but broadly this is what is the dual nature. Okay, so the main things that we have covered in this chapter are what? One, the particle theory of light, the quantum theory, and the support for the particle theory of light, which is the photoelectric emission, Compton effect, Thompson effect, and then the pair production. Then we talked about the wave nature of matter that is proposed by the de Broglie, as per the de Broglie wavelength. Then the experimental observation that supports it, which is the diffraction phenomena explained as per the Davis and Germer experiments, as well as the GP Thompson experimental studies. So this is what we have to cover in total for the dual nature chapter, guys, and mainly the problems, right, numerical questions, if they are coming, they will come from the quantum theory of light, or they will come from the Einstein's equation for the photoelectric emission. So these are the two areas for the numerical questions. Okay, so we will see in the next chapter, which is the atoms. Okay, we will see in next class.